Let's start the afternoon session. The first session is about quantum information. By the way, I'm Xiaoliang Qi from here, and I'm chairing this session. Our first speaker is Professor Joe Polchinski, and from University of California, Santa Barbara. He will talk about the space-time versus quantum mechanics.
So we were asked to speak about where science is going in the next 5 years, and I think that time period was chosen to be maximally difficult. We all know what we're looking for asymptotically, a theory of quantum gravity and everything else. And most of us know what calculations we're going to do and papers we want to read in the next couple of weeks. But there's this in-between period. But fortunately, 5 years is long enough, and I think the time is ripe enough that we're going to make progress on some piece of the big question. So the space-time versus quantum mechanics I'm referring to is Stephen Hawking's information paradox. He argued 40 years ago that black holes destroy information in a way that requires the laws of quantum mechanics to be modified. And 40 years of trying to find Hawking's mistake has only made it clear that what he discovered was really a conflict between quantum mechanics as we've always understood it and space-time as we've always understood it, and that one or the other has to give. And it was his proposal that that it was quantum mechanics that gives. After 20 years, with the discovery of matrix theory and ADS-CFT duality, the conclusion was that quantum mechanics is unmodified, but that space-time is fundamentally non-local. It's holographic. But nevertheless, that this is a sufficiently subtle thing that individual observers will see ordinary local laws of physics. Now, this pendulum has swung a bit higher, though, because a couple years ago, there's this sharper version of the Hawking paradox, which says that in order to save quantum mechanics, in fact, we have to give up much more of space-time. We have to give up the entire interior of the black hole. And so now, the pendulum is kind of in this indeterminate state. We maybe have the firewall, or maybe, well, it seems like we've lost the idea that everybody can be happy, but maybe, in fact, in order to avoid the firewall, we have to start actually tweaking quantum mechanics again, modifying quantum mechanics, not in the way that Hawking described, which would be visible to an observer outside the black hole, but maybe something observable only on the inside. And so over the next 5 years, if not sooner, we need to collapse the wave function of this pendulum. I know many of us think we already know where it's going to end up. I personally see it as being in a quantum state. We need to collapse it as convincingly as the discovery of dualities collapsed the first part of the information problem. So why do we expect progress in the next 5 years? Well, there's a lot of input coming from many different directions. Hawking did not need quantum information theory in order to formulate his paradox, but quantum information theory has, beginning with the work of Hayden and Preskel, done a great deal to sharpen the alternatives and to challenge or to help to construct possible solutions to the original paradox. Again, we have I should have used your pointer, Andre. Next time I'll listen to you. We have this new version of the paradox, but also looking around, there is this just general sort of sense right now that something is happening from many points of view that relates entanglement to the emergence of space-time, especially if you look around. A large fraction of young string theorists these days are calculating holographic entanglement entropy, or are developing this idea, which, by the way, was recognized with one of the Young Scientists Awards this year, developing this idea that there are geometrical constructions of entanglement entropy in terms of the geometry of the dual space-time. But what's not clear, and this is another task for the next 5 years, to understand what this means. Because entanglement entropy is not an ordinary quantum mechanical observable. Entanglement entropy is not something that you could add to your equations of motion. Or if you did, it would really, I don't think anybody would be happy with that because it would really be a breakdown of the structure of quantum mechanics. The other side of this, the geometry, the metric, the curvature, these are things that can appear in the equations of motion. But the quantity of entanglement, just the total amount of entanglement, which is what's mostly being discussed here, can't be. And what really sort of highlights this collision is the ER equals EPR paradox, or proposal of Maldacena and Susskind, the proposal that any two entangled systems have a geometric connection. And so if we put these two spins in the first entangled state there, or in the second entangled state, there's a wormhole between them. But if we put them in either of the two unentangled states, there's no wormhole. Now, in conventional quantum mechanics, the metric is a linear operator. And any observable would be sort of a projection operator that the metric lies within some class and not within some other class. And that's still a linear operator. But now, if there's any projection operator that, say, annihilates the two no wormhole states, it also annihilates the two superposed states. And so there can't be a projection operator onto the metric that somehow measures whether that metric has a wormhole in it. When we went from, now of course we no longer believe that metrics are fundamental, things are holographic, but I think my assumption at least was that this meant replacing the metric with something more mysterious and non-local, but within the framework of normal quantum mechanics, and this goes outside it. Said in another way, one can have states whose physical interpretations are completely orthogonal, a wormhole or no wormhole, but whose state vectors are not orthogonal. That's the same modification that one is talking about. So what does this mean if ER is or is not equal to EPR? So ER equals EPR means that if you have a geometric connection, you have the Einstein-Rosen bridge between two black holes, then the black holes are in an entangled state. This is one of the most secure things we know. Here we have a nice calculation. It's very beautiful. It's derivable from other things that we understand. But as I said, taking this in the other direction, arguing that whenever there's entanglement, there's a geometric connection seems to violate standard quantum mechanics. But if the alternative is also a challenge, because if entanglement does not imply a connection, then you have sort of, if you look, you go from ER to EPR, from connection to entanglement, and back again, and somehow it doesn't come back to where it started. What this means is that on the geometric side, there have to be extra degrees of freedom which are not visible in the dual conformal field theories. And in fact, this was proposed very early on by Marolf and Wall. And so what are these additional degrees of freedom? And this, of course, if it's true, brings up a broader set of questions. Namely, we're always trying to leverage our understanding of the boundary CFTs to understand what's happening in the bulk. We gave up. We haven't made much progress in finding an independent, non-perturbative construction of the bulk. Should we still be looking for this? So it's when you have one of the morals of duality is that things tend to be true in a strong sense. If you have equality in one direction, you have equality in the other direction as well. But in this case, this seems to actually require you to give up quantum mechanics. Now, coming sort of back to the black hole and to the firewall paradox, again, there's something similar going on where the way, in order to avoid, if you sort of try to think about the quantum mechanics of the black hole, and you put in basically as a postulate that there's no firewall, and ask where that leads you, you get to something like this construction called state dependence. And the basic idea of state dependence is that you figure out what are the quantum degrees of freedom inside the black hole by how they're entangled with the degrees of freedom outside the black hole, and only by that. And now it's interesting. This is something which hasn't been emphasized, but this proposal really means that the interior Hilbert space of the black hole has no structure at all. Every state is as good as every other state. There's a huge unitary symmetry. U of e to the s, where s is the black hole entropy, because you need this symmetry in order to implement this proposal, in order that entanglement alone is the thing that determines the internal degrees of freedom. And that's, again, that leads to problems. So here's a typical state, which according to the rule should have no firewall. But then what about this state where we just flip the sign in the superposition? It's as typical as the one anyway. It's as typical as the one above. And therefore, on that ground, should have no firewall. But we can relate those two states just by flipping the external visible bit. And so it seems like an excitation of what I called psi sub 1. So one has a single state with two distinct physical interpretations. It may, in fact, this proposal has been refined to argue that by looking at very tiny corrections, you can distinguish the states with different interpretations. But again, you're in this situation where you have states that have orthogonal physical interpretations and yet are not orthogonal. In this case, are very nearly parallel, maybe even exactly parallel. And in this discussion, I really should recognize Don, Raphael, and Dan, whom I've dubbed the defenders of quantum mechanics. Because in this subject, it's very easy to say reasonable sounding things that make no sense, or at least are taking you, unbeknownst to yourself, outside of the rules of quantum mechanics. And I guess one of the things that I will spend the next 5 years doing is alongside these three, defending quantum mechanics, not necessarily because it won't be modified, but insisting that any modification of it satisfy the same kind of completeness and consistency that our current quantum theory has. So in particular, for this state-dependent proposal, with these two states that are not orthogonal, but that are physically but not mathematically orthogonal, there are some thought experiments you can do. What if you prepare a black hole in a superposition of them? Or slightly more elaborate, what if you prepare them what if you entangle the system with an observing apparatus, in this way that again involves these two closely related states? What does an infalling observer see? And these are the kind of challenges that a more complete theory has to solve. Now, complexity is a refinement of this that I won't have much to talk about, except just to mention something by contrast. I emphasized how this state-dependent proposal has this enormous symmetry on the internal Hilbert space of the black hole. With complexity, there is more structure. There is a definite set of bits. And so it's different. There still is maybe a large U2 to the S symmetry or something, but it has more structure. Correspondingly, perhaps it has more firewalls, but it still modifies quantum mechanics. It still needs to answer arbitrary questions about arbitrary thought experiments. So I'll conclude with a slide of big questions and a slide of little questions. So for big questions, there's an underlying question is, what is the fundamental object in a theory of quantum gravity? Is it a wave function? And if it's a wave function in a universe that has different causal patches, or even an inside and outside of a black hole, how are different observers related? Do they see different pieces of the wave function? Do they see the same piece in different frames? And if so, how are the frames related? So if nonlinearity is, if this violation of linearity of quantum mechanics is coming in, maybe the relation between frames is what's nonlinear. Or maybe even does each observer have their own wave function, but that's kind of bad because it means that the wave function is subordinate to something else, some kind of causal structure that was there first. What are the basic bits that appear in the wave function? What determines the wave function? How is the wave function connected to observation? So there's this Born rule thing, which always comes up, which maybe can be derived if you make enough assumptions. And maybe most of the structure of quantum mechanics is surviving, and it's the Born rule, the interpretation that has to be modified. So those are the big questions. And the small questions are, of course, the next 5 years begin with next week. So what are interesting short-term questions? So we've learned a lot from ADS-CFT duality, and there's an interesting constructions with ADS-CFT, which have some of the same puzzles as the ER equals EPR paradox, but in a single anti-de Sitter space, we thought we understood the complete quantum mechanics. Again, I focused on the idea that the pendulum was going to end up in the bottom with space-time and quantum mechanics both modified a bit. But in fact, maybe we'll end up with a firewall, and then we need a mechanism. And there's interesting ideas from the fuzzball community that there's some kind of entropic pressure driving brains to the horizon, or maybe stringy effects. We've always relied on the nice slice argument, the idea that evolution in the black hole background could be formulated in a way that involved only small curvatures and small energies. But we don't really know that strings can be quantized in a nice slice frame. Maybe there is some stringy physics that we haven't successfully understood. Anyway, a task for the next 5 years to figure out precisely what can it mean for entanglement to be an order parameter for the emergence of spacetime. Clearly, entanglement is an order parameter for lots of things, but in condensed matter systems but there one has additional information. One knows that there's a Hamiltonian that's fairly local, and one is looking at the ground state. So it's not just entanglement that you're using, as in some of these other constructions. And just my own personal problem that I'll throw any number of graduate students at, derive the dualities, which are giving us so much of our leverage. OK, so some big questions, some small questions, and thank you.
Thanks, Joe. Questions? Yeah.
Joe, would you be happy with the theory? Would you be happy with a theory which has nonlinearity only for global properties of things behind the horizon, but anybody who falls into the horizon sees linear quantum mechanics because they're bounded by a causal patch?
So, I'll actually stop your question. I would be happy with a theory, because so far we're dealing with scenarios. We're dealing with frameworks that a theory might exist within, and any theory that has some kind of reasonable logical coherence and which answers arbitrary questions.
Yeah, I know.
Yes,
but I'm asking you a very specific question.
No, I'm a defender of quantum mechanics not because I love it, but because I insist that whatever replace it be.
Would you consider it a violation of quantum mechanics?
It's a violation of our current understanding of quantum mechanics.
It's a violation of your current understanding of quantum mechanics, which is defective.
Well, okay. It's a violation of Raphael's understanding.
It is also a violation of Raphael's understanding.
Yeah.
Would you be happy?
I would be happy. I was prepared to be happy with Papadimos and Raju.
I don't understand. Okay.
It violates quantum mechanics in not the same way, but my problem with it is that in the end there's a long list of questions it can't answer. It's not a theory, and it can't become a theory.
Let me come back to the nonlinearity in global issues.
Yes.
This goes back, I think, to 1993, when somebody or other pointed out, I think it was John and myself, John Preskill, that if you want to have a global description of a black hole, both the interior and the exterior, you're going to have to live with cloning. You're going to have to live with cloning, and you can take two attitudes about cloning. One is a sort of the tree in the forest view. If it happens but nobody can see it, it doesn't happen. And the other, which I think may be a more fruitful view, is to say, in a global description, cloning happens, it's nonlinear, but it's restricted to happen only in separate causal patches. That seems to me to have been there since 1993. And it's not a new issue.
Right. So I thought, well, maybe you see this as this, well, these are your papers, so maybe you see them as continuous with 1993.
Yes, I do.
I think many of us interpreted those ideas, again, as something that could be understood as a violation of locality within linear quantum mechanics. Now, maybe we have to go back and read your papers more carefully.
I would say so.
Okay.
Is the firewall paradox in there too?
No.
It's a really interesting discussion. Maybe I should give a chance to. Is there any other? Yeah.
Well, since that discussion, I can't resist saying Lenny should read his own earlier papers more carefully on longitudinal string spreading, which, if it's correct, gives drama for a late observer. We can show this very clearly kinematically with my student Matthew, and that's why there's some hope for the stringy effects, and at least they should be checked.
Okay, so considering the time, maybe let's thanks Joe again and give more questions.